Hi everybody. Welcome to your first video on the derivative. So this video is titled Definition of the Derivative, but before we get to that, I want to talk a little bit more about tangent lines and the tangent line problem. Okay, so in class we've been talking about tangent lines and secant lines, and remember we defined tangent lines as a line that intersects a curve at one point, and we defined secant lines as lines that intersect a curve at 2 points. Well, I just wanted to clarify that, although we define the tangent line as intersecting the curve at 1 point, in some cases, the tangent line could intersect the curve at more than 1 point, but when we're finding the derivative, we're really just interested in that single point where the tangent line intersects the curve. So here are a couple possibilities. Now, if the graph is a parabola, like in our first graph here, then your tangent line, does only intersect the curve at 1 point. And if you look at the second graph, same idea, the tangent line intersects the curve at 1 point, but notice in this case it actually goes through the curve, where in the case of the parabola, the tangent line is above the curve. In the second graph, the tangent line is above and below the curve. And then in our third graph, we might be interested in this point here and the fact that the tangent line intersects the curve at that point, but technically if we kept drawing the tangent line, which it is a line, so it does keep going, it would eventually intersect the curve again, okay? So I just wanted to clarify that, we define it as a line that intersects the curve at 1 point, but in some cases it could intersect at more than 1 point, but we're typically just interested in that single point, okay? All right, so this is going to be a quick recap of what we did in class today in our exploration. So remember that the concept of the derivative came about when mathematicians were trying to solve what is called the infamous tangent line problem. And so the idea is if we are given a graph of a function, and we're just calling it f of x, and let's say we pick a point on the graph of f of x. If the tangent line problem would be, if I draw a tangent line through that point, the problem is, how do I find the slope of that line when I need 2 points to find slope, okay? So this is kind of the solution that came about to solve that problem. Well, we know we need 2 points to find slope, so let's say that I use the point where the tangent line intersects the curve, but then I just pick some other point on the curve. So if I draw this line, this would be considered a secant line because it intersects the curve twice. Now, I can easily find the slope of that line. Let's say that I call this x-coordinate x, and I'm going to call this x-coordinate x plus h. So then, therefore, the distance in between those 2 points is h. Okay? Then I could come up with 2 ordered pairs, now one for each point, where this point would be x f of x, and this point would be x plus h, comma, f of x plus h. So then if I just use regular slope formula, we know the slope of the secant line is f of x plus h minus f of x all over x plus h minus x. And then we can simplify this because in the denominator, the x's cancel. So this becomes f of x plus h minus f of x all over h. So that would be the slope of the secant line. Okay, but then the question is the slope of the red line going to be a good approximation of the slope of the blue line? Like, are those values going to even be close to each other? Well, I mean, they're both positive in this case, but they're probably not close enough for what we want. So we want to try to get as close as possible, okay? Okay, so the idea is to get a little bit closer to the tangent line, the slope of the tangent line. Why don't we move the point closer? And so now this is the secant line. You know, would the slope of the secant line now be a better approximation to the slope of the tangent line? Well, it's probably better, but it's probably not exactly what we want. It's not close enough. So then the idea is, okay, well then let's just move it closer. So let's say this is our tangent line and our secant line. Now they're almost identical to each other. So we don't even see the secant line anymore, okay? So then the question becomes, okay, as we move the points closer to each other, what is happening to h? Well, remember, h is the distance between the 2 points. So hopefully you can see that h is getting smaller and smaller and smaller. So another way to say that is h is approaching 0, which I hope that sounds familiar. It sounds like a limit that we covered in Unit 1, okay? So the idea is it leads to what is called the definition of the derivative. That essentially is a limit problem. We end up with this definition. We're going to take the limit as h approaches 0, which just means that we're moving the points closer together, and so eventually the secant line will become the tangent line, and we'll get a really good approximation of the slope of the tangent line. And then the f of x plus h minus f of x all over h is basically just slope formula, slope of the secant line. Okay, now there is a slight, different form of the definition of the derivative, which is this. The limit as x approaches c of f of x minus f of c all over x minus c. The only difference here is we would be given a value for x, so like you might be finding the derivative of f of x at x equals 4, and so in that case c would equal 4. But anyway, it's just a slight different take on the same concept. So I'm not going to get bogged down in that too much, but you do want to be familiar with both notations or both derivative definitions. Okay, but the other thing that's really important is that you, in your mind, connect derivative to slope of the tangent line. Okay, so the graphical interpretation of the derivative of a function at a point equals the slope of the tangent line to the graph of the function at that point. And because slope is a rate of change, since we're finding slope at a single point, we sometimes also call this an instantaneous rate of change. Okay? Different from average rate of change. Average rate of change would be slope of the secant line, and instantaneous rate of change would be slope of the tangent line. Okay, now let's talk a little bit about notation, because we have a lot of different ways to notate a derivative. So one way is to use the prime symbol. So like if you were finding the derivative of y, you would just call it y prime. If you were finding the derivative of f of x, you would just call it f prime of x. Then we also sometimes use this notation dy over dx, which means the derivative of y with respect to x. Okay, dy over dx, the meaning of it is the derivative of y with respect to x. And then instead of dy over dx, sometimes we'll just put this d over dx in front of the function. Sometimes this d over dx is called the derivative operator. And then sometimes instead of f of x, we might use y to identify the function. Okay, so these are all different notations for the derivative. Okay, moving on. Let's look at a couple examples. So let's say we're given f of x equals 3x minus 1, and we're asked to find f prime of x, which again means find the derivative of f of x. So for this problem, if you think about the meaning of the derivative, you actually don't have to do any calculus, because f of x equals 3x minus 1 is a linear function. So remember, linear functions have a constant rate of change or constant slope. So the slope of this line is the slope of the tangent line. Okay, so here f prime of x would just equal 3. Because the function is linear and the slope is 3, and that would also be the slope of the tangent line. So really look at your function. You may not have a lot of work to do. Now, let's look at example number 2. This time we're given a quadratic function. So this one's going to take a little bit more work. We're given g of x, and we want to find g prime of 3. And then we also want to write the equation of the tangent line. Okay, so let's start with our definition of the derivative. So the limit as h approaches 0 of, and I'm just going to use g instead of f. So this will be g of x plus h minus g of x all over h. So this would equal g prime of x. But since we want to find g prime of 3, well, we're just going to replace x with 3 in our definition. So this will become g of 3 plus h minus g of 3 all over h. Okay, now we have a little bit of work to do because we've got to find g of 3 plus h. So I'm just going to work that off to the side. G of 3 plus h means we're plugging 3 plus h into g. So this will be 3 plus h squared minus 2 times 3 plus h plus 1. All right, we're going to FOIL 3 plus h squared. I'm just going to do that in one step. We'll end up getting 9 plus 6h plus h squared. Distribute the negative 2, so minus 6 minus 2h, and then bring down plus 1. And then let's combine our like terms, so we end up with h squared. And then 6h minus 2h is 4h. Got all those taken care of. And then 9 minus 6 is 3, and then 3 plus 1 is 4. Okay, so this is g of 3 plus h. And then I also need to find g of 3. Do that in a different color. Okay, so g of 3 just means we're plugging in 3 to g of x. So 3 squared minus 2 times 3 plus 1. So we'll end up with 9 minus 6 plus 1, or 3 plus 1, which is 4. Okay, so now we can plug these into our definition of the derivative. Okay, so now we have g prime of 3 equals the limit as h approaches 0 of h squared plus 4h plus 4, because that's what we found for g of 3 plus h. Okay, minus, sorry, turn the color code, minus g of 3, which equals 4. Okay, to cancel or equal 0. So this will become h squared plus 4h all over h. And then we can divide each term in the numerator by h. So this becomes h plus 4. And then finally, we can use direct substitution. And we get 4 for our final answer. So 4 is the slope of the tangent line that intersects that curve when at x equals 3. Okay. All right. You can probably see why mathematicians looked for some shortcuts later on. These can get lengthy. But they're just essentially limit problems. Okay. Okay. A couple other things we need to talk about in relation to the derivative. So remember this alternate form of the derivative that I showed you? F prime of c equals the limit as x approaches c of f of x minus f of c all over x minus c. Well, if you think back to our unit on derivatives, this would be a general or two-sided limit. So in order for this limit to exist, the one-sided limits would have to exist and equal the same thing. Okay, so these are your one-sided limits. So for the two-sided or general limit to exist, your one-sided limits must exist and be equal. So because these limits represent the derivative, we call these one-sided limits derivatives from the left and the right. Okay, so we would call these derivatives from the left and from the right. So we're going to look at a couple scenarios and see what happens. So in our first scenario, we want to use the function f of x equals the absolute value of x minus 2. So if you think back to your parent functions and transformations, this would be the absolute value function shifted right 2. So it'll look like this. Okay, so let's just say that we want to find the derivative when x equals 2. Well, we have to start with our one-sided limit. So let's say we find the limit as x approaches 2 of this function. And we're going to start with from the left. Okay? Now, since I know that your absolute value function is basically made up of linear functions, we can just find the slope of each line. And so in this case, I need to rewrite this limit. Because we want to basically find this limit, because we're really trying to find the derivative here. So this would end up being the absolute value of x minus 2 minus f of 2, and f of 2 minus 2 is 0, absolute value 0 is 0, all over x minus 2, okay? That's ultimately the limit that we're trying to find. But based on the graph, remember this limit represents the derivative, which is slope. Okay, so what is the slope of this line here? Well, the slope is -1, because you go down 1, right 1. Okay, so this would equal -1. Okay, so let's find the limit. Now we're finding this limit, which again is a derivative, as x approaches 2 from the right. So again, because we know this is a derivative, which is slope, we can just find the slope of this line, which in this case would be +1, because we go up 1, right 1. So our conclusion then would have to be that the limit as x approaches 2 of the absolute value of x minus 2 over x minus 2 does not exist because your one-sided limits are different and they have to be equal, okay? So what we basically have discovered here is a case where the derivative does not exist. And so this is going to happen anytime you have a sharp turn or a sharp corner in the graph of a function. The derivative is not going to exist at that point because your derivative from the left and the right are not equal, okay? All right. One other scenario we want to look at. So this time we're going to use the function f of x equals x to the 1/3 power, which actually is the same as the cube root of x when x equals 0. Okay, so if you think back to your pair functions, this graph looks something like this. And maybe I can do a better job of that. Something like that. Okay, so we're essentially going to do the same thing. We're going to find the limit as x approaches 0 from the left of f of x minus f of c, so cube root of 0 is 0, all over x minus c. So this will just simplify to cube root of x over x. And actually, I could even simplify that, but that's okay. We know this is a derivative, so let's think in terms of slope. So if we're thinking in terms of, well, actually, you know what? I'm just going to make this a general or two-sided limit in this case. The problem that we're leading to here is that this limit does not exist. And so what's happening in this graph is that there is a vertical tangent line when x equals 0. So right when x equals 0, this graph actually does go vertical. And so remember, the slope of a vertical line is undefined. So this is another case where the derivative does not exist whenever a graph has a vertical tangent line. And that's all I was trying to show you there. Okay. All right, so all of this is kind of leading up to this important relationship between differentiability and continuity. Okay. If a function is differentiable at a point, then we know that it is continuous at that point. But it doesn't work the other way around. In both examples that we used, these are both continuous graphs. Like, there's no whole vertical asymptote. Like, both of these graphs are continuous. Okay, but we were able to locate a value of x where the derivative did not exist. So in this case, the derivative did not exist when x equaled 2, and then in this example, the derivative did not exist when x equals 0. So just because a function is continuous does not mean it's differentiable, okay? So this only works one way. If a function is differentiable, then you know it's continuous, okay? But if you know a function is continuous, that does not mean it's necessarily differentiable, because the graph could have a sharp corner or it could have a vertical tangent line. All right, so you guys, we're going to stop the video here, and we will practice using these definitions in class a little bit more. Thank you for watching.